Okay, so we've already looked at how a complex number can be thought of as a point in a plane. So if you imagine z being a complex number, then the way you would plot that number is you would think of the real part A as the x coordinate of the point, and the imaginary part B as the y coordinate of the point. So you would find your coordinate A and your other coordinate B, and this would be where z is, A plus bi. Now it's written differently from a point because it doesn't have the parentheses and the comma, but it behaves in all respects as a point would, in that it has two pieces of information to describe where it is in space. And so you can get to this point z not only by moving in the horizontal and vertical, which is A plus bi, but you could also get to it from finding the angle, whatever the angle is, and going directly there, taking the hypotenuse. So you can get to z using polar form, using polar coordinates. And that's another way to describe this complex number. So how would you get to this point? Well, we've already learned how to find the distance in this direction and the distance in this direction when you're given r and theta. So it's really just r times the cosine of theta as A, and r times the sine of theta as B. Now, people have rearranged this in different ways, and one nice way to rearrange this is to factor an r out, since r is common. You can write it as r times cosine of theta, and then people typically don't want to think of this I being inside of the sine, so they write it in front like this, I times the sine of theta. So that's called polar form. This is polar form. And this one over here is rectangular form or Cartesian form. Rectangular form for complex numbers. And it's identical. This r and this theta are exactly the same as the magnitude and the angle when we were talking about vectors. You can think of this as magnitude, magnitude, and same theta, same symbol, angle from vectors, or as r and theta are distance from the origin and angle from polar coordinates. It's exactly the same thing. We've done that. This is like the third time we've gone through a magnitude or distance and an angle. One thing to note is that this r, this number here, is often called the modulus of z. This is pronounced modulus of z. And how would you get that distance from looking at A and B? Well, since r is the hypotenuse of this triangle whose lengths are A and B, you would simply find it with the Pythagorean theorem. A squared, square root of A squared plus B squared. And then how do you find this particular angle? How we've been finding this angle all along has been from the inverse tangent of B over A, which is the slope of that line. This is inverse tangent. And you have to be careful with inverse tangent, as you've been careful with it before, because sometimes it gives you the angle in the wrong quadrant. So you have to sometimes add pi to it so that it is in the correct quadrant. Also, this is undefined if it's ever on the imaginary axis. If it's ever some multiple of I, then b over a ends up being some number divided by 0, which is undefined, but you can find this angle if you plot it. 5i would be 5 cosine of 0, excuse me, cosine of pi over 2, sine of pi over 2. This angle would be pi over 2 because it would be pointing straight up. So let's do a couple examples of converting a number from rectangular form to polar form. We're going to take a complex number. We're just going to put a and b in, put different numbers in, and find r and theta. Okay. Right. The polar form for z equals, let's do -1 plus I. That seems to be a pretty simple one. Okay, so if we were to plot it, let's plot it over here. -1 and +1, so that's right here. Here's z equals -1 plus I. It's 1 unit up, 1 unit to the left. So I need to find first the angle. So the angle would be this angle, theta, and the distance, which is r, to determine what what this form would look like. R cosine theta plus I sine theta. So r is equal to the square root of 1 squared, well, it's -1 squared, plus 1 squared. Now, it might be tempted to write I here for 1, but this is calculating an actual length, and the lengths are physical, real-world quantities, not complex quantities. So the lengths of this right triangle are going to be 1 unit and 1 unit. So 1 squared plus 1 squared, which is √2. And then to find the angle theta, I know that the tangent of theta is equal to, well, I can just do inverse tangent. Tan inverse of, what is this, 1 divided by -1, which is tan inverse of -1. This is one of the inverse tangent quantities I should know, because it's got a slope of -1. The ones that have slopes 1 and -1 are nice fractions of pi. We know exactly what those angles are. So in this case, if I think about this is pi over 4, 2 pi over 4, 3 pi over 4. This is equal to 3/4 of pi. So here's my angle, and there's my magnitude. So this complex number z is just equal to, let's do it in red, why not? Blue. Square root 2 cosine of 3/4 pi plus I sine 3/4 pi. And that's another way to describe z, using a magnitude and an angle instead of a distance in the x and a distance in the y. How might you convert this back? Good question. Well, you just calculate each of these cosines and multiply them by √2. Hopefully, you end up getting -1 plus I. Cosine of 3 pi over 4 ends up being -√2 over 2, multiplied by √2, ends up giving you -1. Sine of 3 pi over 4 is positive √2 over 2. Multiply that by √2, gives you +1. And so it does, in fact, give you what you started with if you calculate and distribute the √2. Okay, super.